If you look at how traditional databases operate, they all share a single glaring vulnerability: absolute reliance on a central authority. All data and all trust flows through a single point of control. If that hub fails or is compromised, the entire system collapses. The engineering solution to this single point of failure is distributed ledger technology. Instead of storing information in one central server, the database is duplicated and spread across a massive network of independent computers. Blockchain is a highly specific implementation of a distributed ledger. It is designed to solve a very particular problem: how to execute secure, peer-to-peer interactions without forcing those peers to trust a middleman. This map outlines the actual architecture of a blockchain. It relies on a precise combination of established computer science principles. Looking at this system, you can see it relies on 4 mandatory pillars to function: blocks, nodes, consensus mechanisms, and the blockchain ledger. To understand how this architecture guarantees data immutability without a database administrator, we have to construct the system from the ground up, starting with its base mathematical building blocks. On this map, we begin with the foundational unit of the network, the block. Structurally, a block splits into 2 distinct sections. You have the payload, which contains the actual transaction data, and you have the header, which holds the metadata for that specific block. To secure this data, the system runs it through a cryptographic hash function known as SHA-256. This is a one-way mathematical process that digests the block's entire payload and compresses it into a fixed-length string of characters. This creates a mathematical phenomenon known as the avalanche effect. If you change a single bit of information in the transaction data, flipping a single 0 to a 1, the resulting output hash completely scrambles into an entirely new string. Because of this extreme sensitivity, the output hash serves as the block's unique identifier. If the data is tampered with, the resulting hash mismatch becomes a mathematical proof of corruption that the rest of the network will immediately reject. This leads us to the chaining mechanism itself. When a new block is created, the header of block 2 must contain the exact specific hash generated by block 1. That prior hash is embedded directly into the new block's metadata. This sequential link creates the system's strict immutability. If an attacker attempts to alter a transaction buried in block 1, the avalanche effect changes block 1's hash. That instantly shatters the cryptographic link to block 2 and invalidates every subsequent block in the chain. To successfully forge a record, an attacker wouldn't just have to rewrite one block. They would have to recompute the math for the entire chain simultaneously. By locking data together mathematically, the system ensures that once a record is written, it is permanently verifiable. No central database administrator is required to maintain the integrity of the information. Moving to the right side of the architecture, we can examine how these secured records are distributed across the network. The ledger is maintained by a peer-to-peer network of independent computers, known as nodes. Every time a new block is verified, the updated ledger synchronizes identically and simultaneously across all participating nodes. Not all nodes carry the same workload. Full nodes download and store the entire historical ledger, while light nodes store only the header data and rely on the full nodes for transaction verification. The architecture allows for different access permissions, and the rules determining who is allowed to operate these nodes dictate how the network can actually be used. Public blockchains, like Bitcoin or Ethereum, are permissionless. They are open to anyone. Any individual can operate a node, read the ledger, and write transactions, creating a fully decentralized environment. Conversely, private and consortium blockchains restrict access. Only vetted, pre-approved organizations are granted the cryptographic keys required to operate a node and participate in the network. This graph plots a direct architectural trade-off. Private networks sacrifice true decentralization. In exchange, by limiting the number of participants, they achieve much higher transaction throughput and maintain corporate privacy. While the network topology decides who can access the ledger, it doesn't solve a deeper operational problem. The network still requires a way for these independent nodes to resolve conflicting data and agree on the true state of the ledger without a central referee. Looking at the bottom left quadrant, we find the final functional pillar, consensus mechanisms. In computer science, distributed networks face the Byzantine generals problem. This is the distinct challenge of getting multiple independent parties to agree on a single universal truth, even when some of those parties might be offline, broken, or actively malicious. The original solution to this problem is proof of work. In this model, nodes, called miners, compete against each other. They must expend heavy computational energy to solve complex cryptographic puzzles to validate the next block. Because solving these puzzles requires physical electricity and hardware, an attacker would have to amass more computational power than the rest of the entire network combined to force a fraudulent block through. The security is incredibly robust, but the physical cost is steep. Proof of work requires massive energy consumption, and the time it takes to solve the mathematical puzzles severely limits the network's transaction speed. The primary alternative is proof of stake. This model completely eliminates computational mining. Instead, participants act as validators by staking or locking up their own digital collateral to earn the right to propose the next block. The security model here is economic. If a validator acts maliciously and attempts to verify a fraudulent transaction, the network automatically destroys their staked collateral. It enforces honesty through severe financial risk, while requiring a fraction of the electricity. Measured. The main criticism of proof of stake, however, is that it inherently favors those with existing capital. Entities with the most tokens can stake the most collateral, giving them disproportionate control over the network. To optimize for speed, some networks use delegated proof of stake, where token holders vote for a small, consolidated group of delegates to validate transactions, maximizing throughput. And in closed environments, enterprise networks often use practical Byzantine fault tolerance, which relies on a strict supermajority vote among known entities, rather than capital or computation. Regardless of the specific mechanism, these protocols act as the engine of trustless networks. They force disparate, independent nodes to mathematically agree on reality, carefully balancing the trade-offs between energy cost, network transaction scalability, and system security. Looking at the complete map, the architecture functions as a cohesive unit. Cryptography strictly secures the data. Distributed nodes ensure the system cannot go offline, and consensus algorithms guarantee universal agreement. This immutable architecture provides the necessary environment for autonomous logic. Because the network guarantees that the record cannot be altered, it can host code that is similarly tamper-proof. This is the foundation for smart contracts. A smart contract is self-executing code hosted on the blockchain. Because the code itself is stored on the immutable ledger, its logic cannot be changed or interrupted mid-execution. This ensures a deterministic result, automatically triggering actions the moment predefined conditions are met. There is no room for human interpretation. If the code executes, the assets transfer, completely bypassing the need for traditional intermediaries, like lawyers, notaries, or clearinghouses. This specific capability has generated the decentralized finance sector, where complex lending protocols and asset trading are fully managed by autonomous code. It also strictly optimizes cross-border remittances. Value can move from one hemisphere to another, settling finally and securely in minutes, rather than languishing for days in the traditional correspondent banking system. Today, billions of dollars in transaction value are processed algorithmically every day, entirely routed around traditional financial choke points. Ultimately, this architecture rewires how digital systems verify truth. By combining advanced cryptography with peer-to-peer networking, it provides the strict mathematical infrastructure required to automate trust on a global scale.